Alright, SPH3U, this is video number 6. It's about nuclear energy. We already did this one in class, but this is for you guys to review and have my thoughts about it and stuff like that. I am really into talking about this stuff, so I'm going to try to hold myself back, but I might get too excited. So let's talk about what we're talking about. First off, nuclear energy. Just what it is, and defining fission and fusion. It's something that the curriculum wants you to compare. Then we'll talk about the strong and weak nuclear forces. That'll be the fundamental forces. You can see that up here in the keep in mind that you have to know all 4 fundamental forces and their relative strengths, and we're going to get into that there. And we'll talk about isotopes and decay mechanisms. Those of you that have taken grade 11 chemistry will already know a little bit about isotopes. We will talk a little bit more about them. If you've ever wondered why are they radioactive, what is it about them that makes them radioactive, we'll answer a little bit of that question. And then finally, a brief little intro to binding energy. That's all I really want to get through today. I want you guys to be able to understand just the basics of this stuff. This is an incredibly deep topic, and probably a lot of the stuff I'm going to say is going to be deeply unsatisfactory because a lot of this stuff just comes from observation. Like half-lives, for example, they just decay after a certain amount of time. And there are equations that can kind of predict them, but they're extremely complicated. You need years and years of physics and years of math and statistics to actually even hope to understand the equation. So, I don't understand them either. So I'm just going to give you the what. There's a deeply unsatisfying lack of why in this lesson, but it sure is fun to talk about. So, jump right in to what is nuclear energy? Well, it's the energy of the nucleus. Right? The nucleus. Here's the nucleus in an atom. It's just the protons and the neutrons, right? The electrons don't count as part of the nucleus. And so when we talk about chemical reactions, right, chemicals are defined by their bonds, and those bonds are made with electrons. So any chemical reactions involve electrons. Nuclear reactions are when the protons and the neutrons get in on it, and they actually start changing. So that's a nuclear that's a nuclear reaction, and nuclear reactions will make nuclear energy. Now, nuclear reactions can also make electrons, so it's not really that safe to say that electrons don't get involved, but they do always involve protons and neutrons in some way, at least the ones we're going to talk about. So here's an example of one. A neutron comes in and hits this uranium-235 nucleus, and the uranium-235 nucleus splits into 2 smaller nucleuses. First it becomes a uranium-236 nucleus, and then it just splits into 2 smaller nucleuses and 3 more neutrons. So the nucleus has changed. The nucleus has reacted. That's a nuclear reaction. That's the first part. Here's fission versus fusion. Fission versus fusion. Fission is when one big nucleus splits into 2 smaller nucleuses, just like that uranium on the previous page. Fusion is when 2 nuclei merge into a bigger nucleus. It is important to note that this nucleus could undergo fission and go back to this. It's just that it's unlikely. It's more likely for a big nucleus to split. It's more likely for small nuclei to combine, because when a big nucleus splits, it releases energy. When 2 small nuclei combine, they also release energy. There's actually a most stable nucleus. The most stable nucleus is iron. There's kind of a couple of elements around this that have extremely stable nuclei, and so when you're going towards iron from either side, you're going to release energy. So hydrogen fusing into helium, hydrogen is lighter than helium, so hydrogen fusing into helium releases energy. So that's how the sun makes energy. Uranium splitting into barium and krypton, I believe. Uranium splitting into barium and krypton, it goes this way. It's also releasing energy. It's going towards iron. But when you get to iron, you can't release energy forwards or backwards. You have to it takes in energy. It's what we call endothermic. You can think enter for endothermic. Heat comes in, energy comes in. So if you want to go, say from helium back to hydrogen, that's going to take energy. This is also how they make all of those, synthetic elements. You might have heard maybe 2 years ago, they finally rounded out the row of the table that we're currently in, and they added like nihonium and muscovium and tennessine, and I forget what the other one was. They added 4 of them. They make those big heavy elements by just taking an existing heavy element and smashing in something else, and hopefully it fuses, and it fuses for long enough for them to get a signal. So that's fission versus fusion. Please note that, again, large atoms can fuse, and small atoms can undergo fission. But most of the time the large atom will undergo fission, and the small atoms will undergo fusion because it releases energy doing that. Yeah, that's fission versus fusion. I think that takes us to, there's nuclear energy and fission versus fusion. We are rolling through this note here. Our next topic is actually the current topic here, the strong and weak nuclear forces. So let's go forward. Strong and weak nuclear forces. These are part of the 4 fundamental forces. These 4 forces explain every single interaction in the world. So we've already seen gravity and we've seen electromagnetism briefly. Gravity is, mass is the quantity that makes gravity, at least in our physics class. Mass is the quantity that makes gravity. Charge is the quantity that makes electromagnetism. But particles have other quantities that we don't normally deal with in everyday life because it's only important in nuclear reactions. So, chemical reactions are electromagnetic in nature. A lot of physics is based on gravity, but we never really see in our everyday lives evidence of the weak nuclear or strong nuclear force. So we're not used to talking about their particular quantities. So this is mass, we all know mass. This is charge, we all know charge. The weak nuclear force, the quantity that's associated with it is called flavor. And it's just called flavor. It's not actually flavor. These particles don't have some kind of taste or something like that. The flavors in weak nuclear also have weird names. The flavors are up and down. Then there's strange and charm. And then the last 2 flavors used to be called truth and beauty, but now they're called top and bottom. So up and down, strange and charm, and top and bottom are the flavors that particles can have, quarks can have, according to the weak nuclear force. And those flavors, the interactions between the flavors, just like interactions between charges or interactions between masses, are what actually create the force. It's weird to think about. But there's a quantity associated, there are rules associated, there's equations associated. So that's flavor. And then the strong nuclear force also has a quantity associated with it. It's called color. And the colors, thankfully, are named a lot better than the flavors. The colors are, red, blue, and green. And then there's also anti-colors. There's anti-red, anti-blue, and anti-green. And there's rules for that too. For example, any particle has to be together, has to be white. So you have to have a red quark, a green quark, and a blue quark together to make a proper particle, like a proton or a neutron. Some particles are made out of 2 quarks, and they have to be a red and an anti-red, because red and anti-red together make white. There are rules for it, but we kind of made it up, right? They're not actually colored, just like these aren't actually flavored, but it's a way for humans to kind of model these weird things. And that's as far as I know. Please don't ask me any more questions than that, because I have not taken any quantum physics in university or anything like that. I could not give you a proper explanation. That's as far as I feel like I need to know it right now, and that's all you're going to get. Let's talk about these forces, though. The weak nuclear force and the strong nuclear force. What do they do, and why don't we really see them in everyday life? The strong force is very, very, very strong. It's the strongest of our fundamental forces. It's actually stronger than electromagnetism, and it's what's holding the protons together against the fact that they are positively charged and they want to rip themselves apart. So they're held together, and then you'd think they would rip themselves apart even with the neutrons' help, but no, they're stuck by the strong force, a completely different force from electromagnetism, and it doesn't care about the charge. It just cares about the color. And so if the color lines up correctly, these guys will get stuck together. Stronger than the electromagnetic force can push them apart. So that's holding the protons against each other and holding the nucleus together in general. It's also the force that holds the proton itself as a proton, the force that binds the quarks together inside the proton. So that's another thing that the strong force does. It's very, very strong. When this breaks, like when the nucleus undergoes fission is that word we just learned, it requires energy. And then you can get a release of energy in other ways. And it's interesting. Then there's the weak nuclear force. The weak nuclear force has this very kind of subtle thing that it does because of this flavor that it has. Flavor, for example, a proton is 2 up quarks and 1 down quark, and that gives it its positive charge. A neutron is 2 down quarks and an up quark, which gives it a neutral charge. And so if you just flip one of the down quarks to an up quark, you end up turning a neutron into a proton, and that's done through a weak interaction because flavor is the weak quantity, is the quantity of the weak force. And that necessarily requires you to kick out the positive charge as a positron. So this positron actually kind of gets made out of nothing to carry away the positive charge. The other thing that comes off of it is a neutrino, also to carry away certain quantities like angular momentum. So that's the weak nuclear force. It's involved in radioactive decay because it can turn a proton into a neutron or a neutron into a proton and do various other things like that. That's how it's involved. Weak force is, though, it's very weak. It's actually weaker than the electromagnetic force, but it's still stronger than gravity, much, much stronger than gravity. It's important because like I said there, it's involved in our mechanisms of decay, our mechanisms of electromagnetic or of nuclear decay, specifically turning protons into neutrons and neutrons into protons and all that stuff. Here's a ranking of them in terms of strength and range. I'm going to pull my camera over here. In terms of strength and range, if gravity was 1, if gravity, which is the weakest force, was a strength of 1, the weak force is 10 to the 25, so that's 10 with 25 zeros after it. That's a lot. It's 10 million, 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 million times stronger. Then the electromagnetic force is actually a whole 10 to the 11 times stronger than the weak force. 10 to the 11 times stronger than the weak force. So it's much, much, much stronger than gravity. And the strong force is the strongest of them. It's 137 times stronger than the electromagnetic force. There's actually a specific number on that one. At a specific distance from the between 2 protons, the strong force is 137 times stronger than the electromagnetic force holding them together. That's important to know, the ranking of their strengths and the relative strengths. Just gravity is so much weaker than the rest. Electromagnetic 10 to the 10 times stronger than the weak force-ish. And then strong force 137 times stronger than electromagnetic. And then I've also got the range. Gravity is weak, but has infinite range. Infinite range. and that's why, you know, the sun can pull on us and we can pull on the moon and stuff like that. The weak force is actually the shortest range force. The range is smaller than the width of a proton because it's just swapping quark flavors, right? It's just changing the flavors of the quarks, which are inside a proton. It doesn't extend past that, or else a proton could make another neutron, like swap and stuff like that, and we don't observe that, so we know that it's a very short range. Electromagnetic is also infinite range, which kind of trips people out because it's so strong. But the thing about the electromagnetic force is there's positive and negative charge. And so at a large distance, the positives and negatives kind of cancel each other out. And they shield each other, so you don't actually feel that electromagnetic attraction over long distances. And then the strong force is the strongest, and the approximate range is approximately the width of a nucleus, which is bigger than the proton. But it doesn't extend much further than that, and that's why we can break up a nucleus. If we get those protons far enough apart, they will suddenly turn to repulsion and fly apart. So, you know, there's this really cool graph here. There's and it's showing the strong force as this red line, the strength of the strong force. And then the electrostatic force as this blue line. Electrostatic force gets stronger the closer you get with the square of the distance. Well, it gets weaker with the square of the distance and stronger with the inverse square of the distance. So if you're twice as close, it's 4 times stronger. If you're, you know, a third the distance, you're going to be 9 times stronger and stuff like that. The strong force has this really weird curve where it starts off repelling when the protons are really close to each other. Then it turns to attracting, an attractive force when the protons are a certain distance away. There's a maximum at a specific distance, about 1 femtometer, I believe. This is in femtometers. Yeah, femtometers. And then very, very quickly goes away. Very, very quickly drops off to basically nothing. Meanwhile, the electrostatic force just keeps on its infinite curve here. And this can kind of help explain why large particles prefer fission when they release energy. Large particles release energy with fission because they might be starting with an average distance between their protons, you know, somewhere around here. Oh, I'm going to move this back down here. Large particles, you know, maybe they're starting with an average distance between their protons around here, and then they just need a little push in order for electrostatic force to take over. Meanwhile, small particles, they can fall further down this strong force rabbit hole down here, this strong force hole. And so if you can get them close enough, they'll release a bunch of energy in fusion. So it's kind of like this graph really explains it very nicely. Yeah, I think that's it for the strong force. Yes, it is. So we're jumping into our next thing, which is isotopes. I'm going to pause for a sec so that I can fix the topic and the keep in mind. And I'm back off pause, and I keep making that on my screen, which is kind of funny. Isotopes. Isotopes are kind of atoms or elements with too many or too few neutrons. Keep in mind that the number of protons is the thing that makes an element an element. So if something's got 6 protons, it's going to be carbon no matter how many neutrons it has. So that's why I say it's too many or too few neutrons. It might actually be more accurate to say it's a bad neutron-proton ratio, because the nucleus doesn't know what element it's supposed to be. All it knows is how many protons and neutrons are in it, and just the strong force and stuff like that. So as an example, carbon-12 is your typical carbon with 6 protons. That's what makes it carbon, and 6 neutrons. So 6 plus 6 is 12. That's why we call it carbon-12. You can also have carbon-13, which if it's carbon, it's still got 6 protons, right? Protons determines what the element is. So it's got 7 neutrons, 1 extra neutron, and that's apparently okay. That's apparently fine. Carbon can have 7 neutrons and still be okay. But if it has 8 neutrons, which is carbon-14, it's a radioisotope. That's just too many neutrons. There are, physics reasons for this that I really don't want to get into. So for you guys, just know that it's got too many neutrons. and that makes it a radioisotope. The same thing happens with hydrogen. Hydrogen can just have a proton, that's normal everyday hydrogen. And then one in every like 7,000 hydrogens in the world, I think, is a deuterium, which is has a neutron along with the proton. That's also fine, apparently. One proton, one neutron is fine. And then an extra neutron, 2 neutrons and a proton, too many neutrons. So that's called tritium, and it's a radioisotope. Radioisotopes will decay and release radiation. So both of these actually decay in the same way because they have too many neutrons. What happens is the weak force comes in and turns one of their neutrons into a proton. Turns a neutron into a proton. Now, charge has to be conserved. So if you want to turn a neutron into a proton, you're gaining a positive charge. You have to create an equivalent negative charge. So an electron gets created and flies off. And we call that beta decay because of historical reasons. So when you're taking this neutron to a proton, an electron also has to get formed. And you see the same thing happening here. The carbon turns into a nitrogen because it's gaining a proton. So now it's suddenly, hey, look, it's a different element because the number of protons determines the number of elements, or determines the element number. So the carbon becomes a nitrogen because like this specific neutron is turned into a proton. You also have to make an electron, and it makes a neutrino. So yeah, that's radioactive decay. That's this specific kind of radioactive decay, which happens often when there's too many neutrons. When there's too few neutrons, the opposite will happen. A proton will turn into a neutron. We also call that beta decay, but we call it beta positive because instead of making an electron, it's going to make a positron. So yeah, it's a nuclear reaction. It changes elements. So this tritium becomes helium-3. It becomes a different element because the number of protons has changed. This carbon becomes becomes nitrogen because the number of protons has changed. Now it's got 7 protons instead of 6. And that's a nuclear reaction. This, by the way, we're going to talk about this in the application lesson, which is the next lesson, but this is what they use for carbon dating because it's turning into a gas and the gas just leaves, which is really cool. So we'll talk about that. Let's get into other decay modes. So what we just learned about was beta decay. Beta decay, where a neutron turns into a proton. Say this neutron became a proton. You have to kick out an electron to do it. It's called a beta particle, just this fast electron. The opposite, beta positive decay, is also called positron emission because it's kicking out a positive electron. That's what a positron is. And that makes a proton turn into a neutron. So when this happens, the atomic number goes up. Carbon becomes nitrogen. When this happens, when beta positive happens, the atomic number goes down because we're kicking out that positive charge. So if this was, say, an unstable nitrogen, it might turn into a carbon. It might go the other way. There's also alpha decay. Alpha decay actually, an entire 2 protons and 2 neutrons, they just leave. They just get kicked out of the nucleus. And this happens, you can imagine, in much larger nuclei that can stand to lose one of those. Especially larger nuclei that have those alpha particles further out, kind of further out of the range of the strong force, and it's easier for them to get kicked off. There's also something called electron capture. And an electron capture, it's a proton that turns into a neutron, so it looks a lot like beta, except it's not kicking out a particle, it's actually absorbing a stray electron. Normally this is prohibited because electrons want to be a certain distance away from the nucleus, but with the right kind of quantum jump, this can actually happen. Yeah, and you get the same thing. You get a loss of number, a loss of electron, of element number. And that releases energy, and the energy comes out as an X-ray. There's also gamma emission. Sometimes the nucleus doesn't actually change, but the arrangement is like kind of, unstable, and there's a lot of energy there. And so it suddenly snaps to a more stable arrangement of protons and neutrons because these things do actually have specific shells and arrangements that they like to be in. And when it snaps down, the energy has to go somewhere. It gets kicked out as a gamma ray. And then the last one is spontaneous fission. In very, very, very rare cases with very, very large atoms, very large nucleuses, the nucleus will just blow up and turn into two daughter nuclei, much smaller daughter nuclei, and often neutrons will get released in doing so. So those are our decay modes. Here's a really good chart of a bunch of different ones. Black is our stable isotopes. So black, they're never going to decay, or at least we've never observed them decaying. Notice that above the line, so this side here is neutrons, this side here is protons. Above this black zigzaggy line, that means that there's too many neutrons, and when there's too many neutrons, like I mentioned earlier, you get beta negative decay, where a neutron turns into a proton, and you have to kick out an electron. That's why it's called beta negative. When there's too many protons and not enough neutrons, a proton will turn into a neutron, which means you have to kick out the positive charge. That's beta positive, and that's a general trend. See that? You won't really get beta positive decay above this line, and you won't get beta negative decay below this line, because that's not the path to stability for these things. I mentioned that alpha, when it actually kicks out a whole alpha particle, tends to happen with heavier nucleotides. Well, there they are. Heavier nucleuses will undergo alpha decay. You know, everything past kind of 82, and there's a few of them down here that will do it as well. Specifically because 50 is a really nice number. Just for some reason, 50 protons and 50 neutrons is a really nice number, especially 50 neutrons. Look at how many isotopes have 50 neutrons. Right, 50 neutrons. We also see the same thing with 50 protons. 50 protons, that's tin. Tin has a lot of stable isotopes. Many stable isotopes. 50 neutrons is also pretty good. 82 neutrons, though, seems to be a very, very nice neutron number. And typically, even numbers are better than odd numbers, especially when it's an even number of protons and an even number of neutrons. Something like 60% of stable isotopes have an even number of neutrons and an even number of protons. If it didn't matter, if even, odd, and odd were all the same, then you'd expect 25% of them to have an even spread, but no, it's 60. And odd seems particularly bad because there's only 5 stable isotopes that have an odd number of protons and an odd number of neutrons, and most of them are down here where the ratio is more important than the number. Yeah, including nitrogen. Nitrogen 14 is one of the odd pairs, because it's got 7 protons and 7 neutrons, and it's the most abundant isotope of nitrogen. Yeah, so different kinds of decay. Fission, spontaneous fission, where the thing just blows up, could only happen way up here when it's a really heavy nucleus, and it's just gonna just explode. And then sometimes it just kicks out a proton, sometimes it just kicks out a neutron. You know, that's one way to reduce the proton number. Yeah, and then there's some unknown ones. Some of them are unknown. Yeah, there's some that mathematically we know are unstable because they have a more stable form they could be in, but we still haven't observed them decaying. So that's another interesting one. All right, on to our next thing, which is half-lives. So a half-life, you might have seen this in math class when you talk about exponential functions, because it's an exponential decay. It's the amount of time that it takes for half of this to decay. So if we start with 500 grams, 85 days later we have 254. It's about half, right? But we see this curious thing where, like, from here to here, it lost 19 grams, but from here to here, it's only losing like 11 grams. So the decay rate slows down as you get less and less stuff. And it's a perfect exponential. It's always a perfect exponential curve when you have enough of these things. And, you know, any sample will have billions of atoms, so you always have enough atoms. Yeah, and it decays. Notice that 481 after 85 days, 245. 462 after 85 days, 235. 444 after 81 days, 226. It's about half each time. Yeah, so it's about 85 days, a little bit more than 85 days for this specific thing. And the fact that it's a perfect curve tells us that it's based on probability. So I'm going to pull up this PHET simulation of radioactive polonium, which turns into lead by alpha decay. It kicks out those 2 protons, 2 neutrons. So it loses 4 from its mass number. I'm going to reset the nucleus and hit play, and you'll see here, see how it's like shuffling a little bit? That's the nucleus shuffling around. And when it shuffles around just kind of off a little bit and it passes this point, that's where the electromagnetic force overtakes the strong force, and it'll decay. So that one decayed very quickly. We'll do a new nucleus, and you'll see that it's probabilistic. It's probabilistic because this one lasted a lot longer. Because it's a chance. It's whatever chance this thing has to get past this line as it's shuffling around. And we reset the nucleus, and let's see how long this one takes. Ooh, longer than that one. Oh, yeah, that one lasted a little bit longer. Past a half-life. Maybe 2 half-lives. Do another one. Reset the nucleus. Note that the lead is still doing the same shuffle thing, but it's not big enough that the alpha particle can actually get outside of this range. So do one more, and ooh, that one was quick. I want one that like lasts a long time. I want one that lasts like a few half-lives. Let's see if we can get one that lasts a few half-lives. Oh, we're at 2. Yeah, that one was pretty good. So you see that it's just random chance. And if we do it with multiple atoms, I'm just going to add a bunch of them. You see that a bunch of them decay early, and then as you go forwards, they're still, each one individually is decaying with that same probability that it had before. It's just that when you start with a lot of them, you just end up with more chance of one that lasts longer. And, oh, that one, this guy here is holding it on. He's holding on. Oh, come on, where's he going to go? Where's he going to go? Come on, do it. Do it. Come on. Come on. Oh, the probability is just not on their side right now. They're like flipping a coin. Oh, there it goes. It's like flipping a coin and getting a bunch of tails in a row. Same kind of idea, right? It's not like the thing knows it has to decay. It's just a chance that the nucleus is in the wrong arrangement and it's going to decay. So that's an important thing for half-life. When you have a lot of them, there's a good chance that you're going to see a decay event. When you don't have a lot of them, then it's just probabilistic. It's just completely probabilistic. But you see that a lot of them decay early, more of them decay late, and that's where we get our half-life from. As I mentioned before, there are some nucleuses that we know are unstable. Oh, we got four that ended up sticking around this time. Oh, down to 3, down to 2. Oh, then they all went at the same time. So see, we just had 3 go all at once because it's a probability. They're not talking to other nucleuses. They're just shuffling their protons and neutrons around, and if it's in the wrong place, it's in the wrong place. So that's radioactive decay. It's probability. Often it's not just a one-step. So like uranium decays to thorium, which decays to palladium, which decays back to uranium, but a different uranium. 238 decays to 234. Then that decays to thorium, then that decays to radium, that decays to radon, that decays to polonium. Notice that this is alpha decay, so kind of a common thing is to jump down by 4. And this is a whole decay chain, a whole chain of decays until it gets to this, lead 206, which is stable. And here's a chart from 1955 to 2012 of the cesium-137 activity in the air. And you can see the cesium activity level going down over time because it's decaying. It has a half-life of about 30 years. So, you know, from 65 to 95, it would decay by about half. And you can see here that it starts at about 10, and it ends up at around 5 ish, because this is a log table, a log scale. So it's a weird kind of scale where each box is actually 10 times. So this is 1, that's 2, that's 3, 4, 5, 6, 7, 8, 9. So 5 is like kind of there, kind of in that 96 kind of area. It's a common accidental release in nuclear power plants, specifically Chernobyl and Fukushima, which are the only 2 really big releases that we've had. It takes 30 years to decay by half. So over time, those areas get less and less radioactive because the cesium is decaying, and all the other things are decaying too. So yeah, that's half-life. And the last piece is a very quick thing about binding energy, and I'm going to pause for a sec to set these up. Okay, and we're back. I've changed the thing. We're talking about binding energy now, and that's actually where the energy comes from, and it's actually related to, you know, this extremely famous equation, Einstein's E equals mc squared. That's actually not the full equation because there's also a momentum term in the real equation. But for things that are standing still, mass is equal to, or energy is equal to mc squared. So E is energy, m is mass, and c squared is the speed of light squared. Speed of light's already a very big number, like 300 million meters a second. So squaring it gives you an even bigger number. So big number times mass is the energy. Which means that that when we change the energy, that actually gets stored or released as mass. And this is true for any energy change, which is kind of freaky. Let me just put that over to the right. There we go. Here we have a helium nucleus. A very strongly bound nucleus, basically an alpha particle. If you want to take this thing and turn it into 2 individual hydrogens, if we look at this graph, from the helium to the hydrogens, you need to put in energy, because going this way gets you closer to iron, going this way gets you further from iron, so you need to put in energy to go this way. So it's an input of energy. And if you take these, the 2 hydrogens and 2 neutrons, 2 free neutrons, and you add up their masses, like you literally weigh them with a particle accelerator basically, you get 4.03 mass units. But your original helium would have had a mass of 4.0026 mass units. So there's actually a change in mass, an increase in mass, because this collection of particles together has more energy than this one did. So the energy went into the mass of the particles. Not, you know, adding mass the way we think of adding mass, you know, like me taking a sip of my water is going to add some mass to my body, but that's adding particles. No, the particles themselves get heavier, which is profoundly weird. And this is true for anything that gains energy, which is really odd. So if anything that gains energy gains mass, if you look up here, anything that loses energy, anything that's exothermic, that one, loses mass, which includes stuff like the sun. The sun is actually constantly losing a bunch of mass just by fusing these hydrogens into heliums, and that release of energy means the sun loses mass. It loses 4 million tons a second to this process, which means that over the course of its lifespan, it's about 5 billion years old. Over the course of that lifetime, it has literally just destroyed, like, not even particles anymore. It's just it turned into energy about 100 times the mass of the Earth. So that's just that many particles just gone, just turned into energy, turned into essentially light radiation. The sun also kicks off like the solar wind, like all those solar flares and stuff you see coming off. that's about 1.5 million tons a second. So the fusion mass loss is actually bigger than the solar wind mass loss, and that's binding energy. Actually, it leads to a change in mass, and you can use this equation to figure out exactly how much mass you're going to lose, or if you know how much mass you're losing, you can figure out how much energy you get. So theoretically, I just told you the sun loses 4 million tons a second. You could take 4 million tons, multiply it by the speed of light squared, well, you'd have to be in kilograms, and you get an energy for how much energy the sun makes in a second in joules. And yeah, that's the end of the content. Let's just go back over what we did. We talked about fission versus fusion in terms of nuclear energy. You have to know the difference between fission and fusion. You have to know that fission of large nucleuses, large nuclei, usually releases energy, whereas fusion of small nuclei is the thing that usually releases energy. Small nuclei can undergo fission, but typically that it requires energy. And large nuclei can undergo fusion, but that also typically requires energy. We talked about the strong and weak nuclear forces. You have to be able to rank the 4 fundamental forces in terms of strength, and then also in terms of range. We talked about isotopes and decay mechanisms, this idea of a bad number of protons and neutrons. I didn't mention it, but apparently 43 is just an untenable number of protons, because that's technetium, and every isotope of technetium is radioactive, which is really weird for such a small nucleus. Like, everything around it is stable, but 43 protons is just apparently horrible. Just a terrible number of protons. And the decay mechanisms, various decay mechanisms that atoms can go through in order to make that proton-neutron ratio come back to a better ratio. So beta negative if you're turning a neutron into a proton, beta positive if you're turning beta negative turning a neutron into a proton. Beta negative turning a neutron into a proton. Beta positive turning a proton into a neutron, kicking out an alpha particle. That's alpha. Electron capture. We talked about that. And then some of the other ones like spontaneous fission. And the last piece was this brief intro to binding energy. This idea that mass, the change in energy comes with an associated change in mass. So mass kind of is energy, is very, very cool. That's some Einstein-y stuff. That's it. I managed to keep myself to like 43 minutes, which I'm very proud of. Good job, Mr. B, for not talking everybody's ear off. If you're interested, there is so much stuff out there to show off. I will put this up in the description if you want to play with the radioactive decay applet. Yeah, thanks a lot, and I'll see you guys in class.